All right, let's take a look at problem number 22 from the 2020 AMC 12A, and it reads, let a sub n and b sub n be the sequences of real numbers such that the complex number 2 plus I raised to the nth power equals a sub n plus b sub n times I for all integers n is greater than or equal to 0. What is the infinite sum of a sub n times b sub n over 7 to the nth power? All right, so let's first start the problem by converting the given complex number from a plus bi form to r cis form. And to do that, we need to find the magnitude of the complex number. And so we can do that by using the formula a squared plus b squared equals the magnitude. And we can do that by simply plugging it in. So 2 squared plus 1 squared equals 5, and then take the square root of that, and that would give us square root of 5. So that means r is going to be the square root of 5. Now we can find out the angle by just sketching a diagram, and we can see that this would be 2 across and this would be 1 up. And so we could say this angle theta is equal to the arc tan of 1/2. Since the opposite side to the angle is going to be 1 and then the adjacent side is 2. Okay, so that means that we can, I'll write the complex number as square root of 5 times cis of theta, and I'll denote theta to be the arc tan of 1/2. All right. Well, we can now substitute this complex number in for 2 plus I, and then raise it to the nth power, right? So if we do that, we will get something like this. And then we can, since these are two different terms that are multiplied together, we can split the exponent to both of those terms. So that would now be square root of 5 to the nth times cis of theta to the nth power. You can also, I guess the standard notation would be that, but you can also write it like this. Okay, well, realize that through the De Moivre's theorem, this is equal to cis of n theta. And by this, I mean just this part, right? Because we know that when we have r cis theta raised to the nth power, this is the same thing as r to the n times cis to the n theta through De Moivre's theorem. So we can use that in this part of the problem. So I can just rewrite this as square root of 5 to the n times cis of n theta. Okay, well, we're tasked, we're essentially asked to find a sub n and b sub n so that we can multiply those two values together. And so we can find the components of this term. And cis of n theta is essentially cosine of n theta plus sine of n theta times I. All right. So now we can distribute the square root of 5 to the n for both of these terms. So I can multiply it there and then multiply it here. So that would give me square root of 5 to the n cosine of n theta, and then here it would give me square root of 5 to the n sine of n theta I. Okay, so we can obviously quickly realize that this would be a sub n, and then this term would be b sub n, and this would be our I. Okay, well, let's now multiply it together since we're asked to find the infinite sum of a sub n times b sub n over 7 to the n. So let's multiply these two terms together. And if we do that, so let me move this across. So when we multiply these two together, so when we multiply these two together, notice that, guess you gotta select it every single time. All right, there we go. All right, so when we multiply these two terms together, we can notice that, and I'm crossing out the I since it's b sub n times I. When we multiply these two together, notice that we are obviously going to be multiplying these two terms. That will give us 5 to the n. And then we will get cosine of n theta times sine of n theta as well. All right. And then this would be over 7 to the n. And we're essentially tasked with finding the infinite sum of this big chunk. So I'll preface it with that. So I'll say infinite sum of starting from n equals 0 all the way to infinity, obviously. Okay, so what can we do from here? Well, remember that sine of 2 theta equals 2 sine theta times cosine theta. And you can see that right here we have cosine of n theta and then sine of n theta. So we can essentially combine it to make 1/2 sine of 2n theta. So once I delete this, and let's get rid of that as well, let's combine these two terms. So if we do that, we will get sine of 2n theta. And we obviously have to preface it with a 1/2 coefficient since there is no 2 cosine n theta. It's just a 1 cosine n theta over here, right? That would be a 1 cosine n theta. Okay, so we can essentially rewrite this expression as being this. The infinite sum, n equals 0 to infinity, and we have 5 to the n times all this over 7 to the n. Okay, well, we can obviously combine these two terms. So when we do that, we will end up with, I think I can move this to the right here. Okay, so when we combine this, we can obviously rewrite this to be 5/7 n. So this would just be 5n, or 5/7 times n, times 1/2 sine of 2n theta. Okay. Well, again, what can we do from here? We sort of simplified it a bit, but we still have this 1/2 sine of 2n theta, and we need to get the infinite sum of this. Well, notice that you can rewrite this as being the imaginary part of e to the 2n theta I, right? Because essentially, we can rewrite any complex number as r to the e I theta. I think it sort of got cut off there, but there we go. R times e to the I theta. So we can rewrite this as being, and by this I mean specifically just this part, we can rewrite that as being e to the 2ni theta. I think I already wrote it up here. All right, so this would be our expression, and we obviously need to get the imaginary part of that because we're not including the cosine of that part since it includes this, right? Because the form of complex number would be this. So we only want this part of it. We essentially want the coefficient of the I term. Okay, so now we can go back and rewrite this. So if I go ahead and erase this out and rewrite this as being 5/7 n times 1/2, and we can move the 1/2 to the outside since it is a summation. So I'll move the 1/2 to the outside and we'll essentially say this is multiplied by e to the 2n theta I, and we'll need to get the imaginary portion of this. We just can't forget that at the end. Okay, well now we can solve for this by obviously using our geometric series formula. So that would just be if we just move this to the outside, the n to the outside, this would essentially just be e to the 2i theta to the n. And so we can combine, we have 5/7, and we can combine these two to make 5e 2i theta on 7 to the nth power. All right. Well, now I can delete all of this stuff. So let's do that. And let's move this over there. Okay. So from here, we can use our geometric series sum formula. And that would just be a over 1 minus r, where a is the first term. We know that n starts with 0, so this would just be 1. And 1 minus r. R is the common ratio, which is just the fraction itself, right? So that would just be 5e 2i theta on 7. All right, so this is the sum. Now, what can we do from here? Well, we can rewrite this expression once again, right? So this is just going to be cis of 2 theta. So now we need to figure out what this would be. Well, we know that the angle is arctan of 1/2. And the complex number on the unit circle that coincided with that angle was, as we denoted earlier, was square root of 2 on 5 plus, or I think it was 2 on square root of 5. It was essentially this complex number divided by the square root of 5, or divided by the magnitude. So we had 2 over square root of 5 plus 1 over square root of 5 as being that complex number. And so when we square that, because of De Moivre's theorem, right? So essentially, cis of 2 theta is equal to cis of theta squared. So when we do this, we will get 4 on 5 minus 1 on 5, which is 3 on 5. And then obviously, we know that using Pythagorean's theorem, this would be our resultant complex number, 3 on 5 plus 4 on 5i. Okay, so from here we can plug this into the equation right here. And so that would just give us 1 over 1 minus 3 plus 4i on 7. Okay. All right. So now we can go ahead and evaluate this. So this would just be, let's look at the denominator first. So the denominator would just be 1 minus 3/7 minus 4/7 I, and that is 4/7 plus 4/7 I. All right. Well, we can now, guess I'll go back and delete all of this. Okay. So obviously go back and we have 4/7 plus 4/7 I, and that's obviously the denominator. And that's going to be essentially multiplied by the conjugate. So 4/7 minus 4/7 I. And so when we multiply that, so I'll say multiply by conjugate, or just denoted by that, this would be 4/7. Guess I'll move it down a bit. But that's fine. 4/7 minus 4/7 I on the numerator. And then this will be divided by, this is the numerator right there, and then this will be divided by essentially just FOIL it out. So this is 16/49. This and this cancels out. So now we're left with this, and that would be negative 16/49 I squared, which is just adding that. So we'll essentially just multiply that by 2. Okay, so now let's evaluate this expression. So we can erase all of this. And now let's go back and evaluate it. So if we divide this from the first term, we'll essentially get 28 on, let's see, so this would be 4/7, and then divided by that would be the same thing as multiplying by the reciprocal. This would be 8, this would be 7. And then obviously you would get the same thing for the second term since it's identical. So your resultant would be 7/8 minus 7/8 I. Okay, well, we know that we want to get the imaginary part of this expression, and that would be 7/8. And we can then multiply by 1/2, and that would give you 7/16, which is your answer.